Hello everyone, Kelton here again. Today we are going to be discussing proteins again, and this time we're going to dive into the topic of enzymes. So pause the video, take a look at the outline, and we're going to get started. Many of you are familiar with the term catalyst, and you might remember that a catalyst is just something that speeds up the rate of a reaction. While catalysts can speed up the rate of the reaction, it's important to note that they do not affect the spontaneity of a reaction, meaning that it doesn't make a reaction more likely to take place if it's a non-spontaneous reaction. Another key point to make about a catalyst is that it's not used up in a reaction. So if a catalyst is something that can speed up a reaction but doesn't affect the spontaneity of a reaction and isn't used up in the process, how do you think these are going to work to help increase the reaction rate? So catalysts work by decreasing the activation energy required. If you look at this image, notice that the reaction on the left is uncatalyzed and it has a really large activation energy. If we look at the image on the right, we notice that the activation energy in the catalyzed reaction is much smaller. This lower activation energy enables the reaction to proceed much more rapidly than the uncatalyzed reaction. In addressing the spontaneity of this reaction, notice that in the catalyzed and the uncatalyzed versions, the reactants and the products have the same amounts of energy. So we see here that the reactants have the same amount of energy, and then we see here that the product has the same amount of energy. So if you remember, the difference in energy between the products and the reactants gives us a value known as delta G. This delta G is going to determine spontaneity. Because a catalyst doesn't change the energy of the reactants to the products, the uncatalyzed and catalyzed versions of the reactions have the same delta G value, meaning that they have the same spontaneity. Moving on to the more biological side of things, what is an enzyme and how does that differ from a catalyst? And nice, so that was a little bit of a trick question. So an enzyme is just a biological catalyst. And we can see that all of the same rules that apply to catalysts also apply to enzymes. The image below gives a really good example of how enzymes work. So an enzyme is going to meet up with a substrate. Once they've combined, they form an enzyme-substrate complex. This enzyme-substrate complex is eventually going to change the substrate into a product molecule, and then they split apart again, once again leaving the free enzyme, and now a new product. So one term that you might have heard me say that you're unfamiliar with is the term substrate. A substrate is simply a reactant used by an enzyme. The active site on an enzyme is just going to bind the substrate. So remember, enzymes are typically made out of protein, so what do you think is going to make up the active site? And perfect, so hopefully you remember the last discussion on proteins where we found that amino acids make up a protein. So amino acids are going to make up the active site of an enzyme. These amino acids are going to be responsible for weakly binding to our substrate molecules as we see here. So hopefully you remember that there are quite a few different amino acids and many of them have specific properties. The specific properties of these amino acids mean that they will only interact with some molecules. This gives us the term known as substrate specificity. This term basically is what the name implies, and that the enzyme will only bind to specific molecules. The specificity constant then is just a measure for how well an enzyme is going to bind to something. So what does it mean then for an enzyme to have a high specificity constant? And perfect, so this is just going to mean that the active site in the enzyme has a high affinity for its substrate. This means the enzyme is going to be highly efficient. There have been a few different models that try to explain how the active site on an enzyme works. One of the earlier models was known as the lock and key model. The lock and key model implied that the enzyme's active site was very rigid and that it didn't move at all. This model has since been discredited. The new model is known as the induced fit model. The induced fit theory basically just says that the active site of the enzyme will change shape slightly to accommodate the substrate. This is the more accurate of the two models. While the majority of enzymes are made of proteins, there are a few examples of non-protein enzymes. One such non-protein enzyme is known as a ribozyme, as we see here. This ribozyme is going to be talked about later on. In order for enzymes to function properly, they often need things known as cofactors. There are two different types of cofactors. Organic cofactors, which remember just means being made up of carbon, and then they have inorganic cofactors, which are typically metals. Organic cofactors are also known as coenzymes. These coenzymes are typically vitamins like biotin or vitamin B12 or vitamin C. Inorganic cofactors are typically thought of as metals like potassium, magnesium, or iron. Holoenzymes are enzymes that are bound to a cofactor. When a cofactor is covalently bonded to an enzyme, we call this a prosthetic group. These prosthetic groups are really tightly bound onto the enzyme. In the image below, do you think you could label which one is a holoenzyme? And great, so the one on the right, which is bound to its cofactor, is known as a holoenzyme. An apoenzyme then is an enzyme that is not bound to its cofactor, and we can see this in this image here. Temperature and pH both affect enzymatic activity. If we look at this image on the left, we notice that this enzyme has an optimal pH. This optimal pH is going to occur where our rate of reaction is the highest, as we see here. As we increase or decrease our pH, we notice that the enzymatic activity begins to decrease, as we see here on the right side and here on the left side with the more acidic pHs. If we look at this image on the right, we see that this enzyme has an optimal temperature at around 39 degrees, which is about body temperature. If we decrease in temperature, we notice the rate of reaction slowly decreases, but if we move to the right and increase our temperature, we notice the reaction rate falls off really rapidly. So why do you think that an enzyme experiences a loss of function when it moves outside of the optimal pH range or the optimal temperature range? And perfect. Hopefully you remember our discussion from last week where we talked about how temperature and pH both influence a protein's shape. When we move outside of the optimal temperature or outside of the optimal pH, we notice that the change in shape results in a loss of function of our enzymes. Last week, we also learned that temperature and heat can be used to denature a protein. This is what we see happening here, and this is what results in this rapid drop-off as the enzyme becomes denatured and thus can no longer fulfill its function at all anymore. Next, we're going to talk about enzyme inhibition. So, what do you think this term might mean? And great, so think whenever we're inhibiting something, we're trying to stop it. So enzymatic inhibition is just trying to slow down or hinder the progress of an enzyme. We're going to talk about two different types of inhibition today: competitive inhibition, as we see here, and non-competitive inhibition, as we see here. Competitive inhibition basically implies that there's competition between an inhibitor and a substrate. We see in this image that the inhibitor binds to the active site, and when the inhibitor is bound to the active site, this prevents the substrate from being able to bind to the active site. One way to overcome competitive inhibition is just to add a lot more substrate. Eventually the substrates are going to outnumber the inhibitors and you're still going to get a good reaction rate. Non-competitive inhibition then means the inhibitor is not going to be binding to the active site. The inhibitor instead is going to be binding to an allosteric site on an enzyme, which we see here. This allosteric site is just another site that isn't the active site on an enzyme. When an inhibitor binds to an allosteric site, notice that the shape of the active site changes. This change in shape means that the substrate is no longer able to bind with the active site. So knowing that non-competitive inhibition changes the shape of an active site, do you think this can be overcome by adding more substrate? And great, so hopefully you piece together that non-competitive inhibition cannot be overcome by adding more substrate. This is because the inhibitor and the substrate don't compete for an active site. Instead, the inhibitor simply deactivates the active site for a while. And great, so now that we've talked about a few things that can affect how fast an enzyme can work, let's talk about enzyme kinetics. A few key terms to know while studying enzyme kinetics are velocity, Vmax, and our substrate concentration. So velocity, as we see here on the y-axis, is just going to be the reaction rate. Think of this as a speedometer on your car, how fast the reaction's going. Vmax is the maximum velocity that an enzyme can reach, and we see that occur here when we kind of see the curve flatten out at the top. Substrate concentration then is just as the name implies, the concentration of substrates that we're using. Notice that as we add more substrates, we see the reaction rate increase, like we see here on the right, the reaction rate's larger than here on the left where we have fewer substrates. So after looking at the enzyme kinetics plot, do you think you could tell me which one of these images shows Vmax, or the point where the enzymes are working as fast as possible? And great, so hopefully you got that the image on the right shows Vmax. At Vmax, our enzyme is going to be saturated with substrates, so adding more substrates isn't going to help the reaction go any faster. When comparing this to the image on the left, we see that the left has very few substrates. This reaction could easily be sped up by adding more substrates, while the reaction on the right isn't going to be benefited by adding more substrates. Another really important term to address when talking about enzyme kinetics is Km, or the Michaelis constant. To put it in simple terms, the Michaelis constant is simply the concentration of substrate when the reaction reaches half of Vmax, as we see here. A large Km means that the enzyme has a low affinity for the substrate or doesn't bind very tightly. A small Km, on the other hand, means that the enzyme has a high affinity for the substrate and it wants to bind really tightly. When applying these terms to competitive inhibition, we see that Vmax is going to stay the same while our Km is going to increase. In this image, we see that the normal enzyme versus an enzyme that is competitively inhibited have the same Vmax. This is going to be because we can add more substrate to overcome that inhibition. In this reaction plot, we also see that the Km for the competitively inhibited enzyme was increased. This is because we had to have more substrate to get to half of the Vmax. When examining enzyme kinetics with a non-competitive inhibitor, we notice that the Vmax is going to decrease while our Km is going to stay the same. When examining this reaction plot, we notice that the Vmax for the non-competitively inhibited reaction is going to be decreased as compared to the normal enzyme. This is because this cannot be overcome by adding more substrate. This plot also does a really great job at showing that at half of Vmax for each of these reactions, the concentration of the substrate is going to be the same. This means that they both have the same Km value. Here we have 3 examples of enzymes that might be useful to know. A phosphatase is an enzyme that cleaves a phosphate group off a substrate, as we see in the bottom half of this image here. In the top of this image, we see a kinase at work. A kinase is just something that's going to utilize a phosphate group from ATP and add it onto a substrate without breaking any bonds on the substrate. A phosphorylase is similar to a kinase, except that it's going to be breaking bonds within a substrate to add a phosphate group onto the substrate. Okay, so now that we've had the lesson, it's time for a mini quiz about enzymes. So, which of the following statement about enzymes is false? If you remember from the beginning of this lesson, we discussed how an enzyme simply acts as a biological catalyst. So this is going to be true, so we can get rid of this answer. Moving on to B then, B says that enzymes reduce the energy of the transition state. So if you remember, the top of the activation energy curve represents where the transition state's at. So if the energy of the transition state is decreased, we then have a decrease in activation energy. So this one looks true as well. C says that enzymes decrease the energy of the reactants. We had said that enzymes do not change the energy of the reactants or the product, so this one looks false to me. Just to be safe, let's take a look at D as well, and D says that enzyme active sites change their shape, and we know this to be true via the induced fit theory. This solidifies C as being the false answer. Remember, enzymes cannot decrease or increase the energy of a reactant or product. Okay, we just had a really dense lesson on enzymes, so let's do a few quick review questions to see what you learned today. First, what type of inhibition can be overcome by adding more substrate? Second, what does a low Km apply as opposed to a high Km value? And lastly, how do enzymes increase a reaction rate? If you can answer these questions, you're well on your way to success. Everybody be sure to have a great day, and I will see you guys in the next one.